So this first application of all that electron stuff, that skills-based stuff, is understanding light. Now, there are several steps that occur for an atom to give off light. One of the favorite labs that students have all year is in about a week and a half. We're going to take different elements and put them in the fire, and they're going to burn different colors. We're like, well, how do they burn different colors? All atoms have electrons. Electrons are the key to why light is given off. Step number one, electrons absorb energy. I can almost write this first slide as a step number two then is they move up what's called energy levels into what's called an excited state. I'll demonstrate this in a minute. So how is light given off? Well, in this room, the light bulbs have a gas in them. That means they're made up of atoms, elements. When I flick on a light switch, electric energy is passing through those atoms. So they have the opportunity to gain energy. When you have a campfire or a candle, heat energy is being absorbed, gained by atoms. When electrons gain energy, they jump. They move away from the nucleus that they're naturally attracted to. We call that an excited state. I would use the analogy of give a little kid a whole bunch of sugar. They all of a sudden move into a very excited state. So you give them energy, sugar, they are now excited. However, just like a little kid that you give sugar to, eventually that kid will come crashing down. Electrons do the same thing. They can't stay excited forever. They will fall back down to their ground state. As they fall down, that energy that they use to jump up is given off, just in a different form. When I flipped on the light switch, electric energy was absorbed by atoms. Same amount of energy, but now it's in the form of light, a different form of energy. When you start a campfire, heat energy is being absorbed by atoms. They give this off in the form of light. That's why a fire has a glow to it. Any electron in an atom can gain energy and jump up and fall down. All electrons in an atom can gain energy, jump up, fall down, which is why we need to be aware of all the electrons, which is why we worked on the mapping out of them. We can point to, oh, that gives off the color red. It's probably due to the 3s electron doing this. Or, oh, that's ultraviolet light, higher energy. That's probably more like the 2p electrons that were doing it for this particular element. So we can find out where these electrons are coming from and going to. You don't have to write this next thing down. But often to help these first two bullet points, to help explain how light's created, we will draw a Bohr diagram. Now I say a generic one because it doesn't have to be for a specific element. So what instead of writing down this last bullet point of words, what I'd like to do is draw a Bohr diagram to demonstrate this. Again, I don't care what element it is, so I'm just going to shade in my nucleus. I'm not going to write down protons or neutrons. There we go. Let's say I have an electron right here in my second shell. If energy passes through this atom and that electron absorbs energy, it can jump up. Again, if it goes to a further away shell, we call that an excited state. However, it cannot stay in an excited state forever. Eventually, it will fall back down, going back to what's called its ground state. Now, I could have one element do that, one electron do that. I could have a different electron jump up just one shell and then fall down. I could have one jump up 3 shells, 4 shells. But the absorbed energy, jump up, fall down. As you fall down, you give off that energy. That is how light is created. It deals with the electrons in an atom, which is why our focus is on the electrons right now. I'm going to go back to the notes. In Unit 1, we gave you the conservation of mass law. Mass can't be created or destroyed. We did labs and activities dealing with start to finish. Mass doesn't change. The same thing holds true for energy. The creation of light is just one of the countless examples of the conservation of energy law. Energy can't be created or destroyed, just transferred from one form to another. So my bullet point, it says the same amount of energy that's absorbed by an electron is given back during that fall. Oftentimes it's just changing the form. Electric energy turns into light energy. And when I turn on the light switch, that's electricity. That energy now is turning into light energy. When I burn a piece of wood, or when you guys in about a week or so burn different elements over the Bunsen burner, heat energy is converted into light energy. It's the same numerical value if we were to calculate that, which is what next class is all about. But it is now a different form. Okay? I hope people still writing. Right. We need to go over something referred to as the electromagnetic spectrum. And what that's referring to is that when light travels, it travels in waves. Different lengths of waves will relate to different amounts of energy and different types of light that are given off. There's a tremendous range in which these waves of light. Some waves of light are really, really long. Some are really, really tiny. Some of that light that's given off by elements we can see. If we can see it, it's called visible light. I'm hoping you know what Roy G. Biv means. Roy is red, orange, yellow, G green, blue, indigo, violet for the Biv. These are the visible forms of light. Within that huge range of wavelengths that I have in the top bullet point, only a small fraction of light that's given off by things can we actually detect with our eyes. From 400 to 700 nanometers. Nanometers. That sounds familiar from Unit 1. You had us do this metric conversion with that. This is the reason why. When we talk about light, the unit of measure for waves of light is in nanometers. Now, we are aware of other forms of light other than the ones that we can see. Some is high energy light. Ultraviolet, which is abbreviated UV. Remember, put on your sunscreen or else you can get a sunburn because of UV radiation. Ultraviolet is a higher form of energy than visible colors of light. X-ray is even higher form of energy. Gamma ray is even higher. So there are some forms of light that are really super duper high energy. There's also forms of light that are lower energy than visible light. IR is infrared. You ever hear of people putting on infrared goggles so they can see the heat given off by people in the middle of the night when they're out doing whatever? Infrared is a wave of light. Microwaves. We will go over how a microwave warms up food. It's due to the waves of light these microwaves given off. Radio waves. You don't think of turning in your radio to like 1015 is actually light, but those signals being sent from station to radio tower to your device, that's a light wave. That's a traveling wave. Okay. So again, light is moving waves. Three terms, or three things dealing with light that we have to become familiar with over the next day and a half is wavelength, frequency, and energy. And I'll show you that in a bit back to our board diagram. But if I were to define wavelength, if you think of waves, it's the distance of one peak to another. How long a wave is, hence wavelength. Frequency is how often it occurs. Anything that's frequent, that happens a lot. What I'm going to do is I'm going to go back to, I'll let you finish jotting this down. I'm going to go back to my board diagram and just kind of show this to you. Here's my board diagram. If blue light were given off during this jump and fall that I've shown on the left, waves of light would be given off. A wavelength is the distance of one wave. I mean, it could be from the peak. It could be from the trough, the bottom of it. It's just one full oscillation, one full wave. On the right-hand side, I have red light given off. It has a wavelength. Which color, red or blue, has a shorter wavelength? John? Blue. Which color, red or blue, has a higher frequency? Al? Blue has more waves. Shorter waves are more frequent. Looking at these two colors here, which one do you think has a higher energy, the blue or the red? What do we think? Listen, the blue. There's two ways you can think about it. Hey, this blue one is moving smaller and faster. Faster means higher energy. That sounds good. Or look at the board diagram. The blue jumped up 2 shells and fell down. The red only jumped up 1 shell and fell down. To jump up higher requires more energy. And then when you fall back down, you're giving off that energy. So this relationship between wavelength, frequency, and energy is something that we have to dive into more next class period still as well. That's what that POGIL packet that we're not going to get to today, that's what that would go over. I have one more slide to finish up. Because unfortunately for you guys, we went from things that I thought were kind of easy, you know, metric conversions and conservation of mass, to complicated things like this electron stuff that we've been doing the last 2 days. And light is actually a little more complicated than just it's moving waves. Because light also behaves like a particle. If you've ever heard the term a photon is referring to a particle of light. So not only do electrons gain energy, jump up and fall down, and give off energy in the form of waves, but they also give off something referred to as a photon, which as far as we know, a photon has basically no mass at all. So it's not like something's losing mass as it's doing this. But it's something referred to as the dual nature of light. Light will sometimes behave like a particle, sometimes behave like a wave. So we want you to be aware of both. Quite frankly, our focus is much more on the wave aspect of it. So electrons also have this dual nature at times. They'll behave in the sense of a particle. Remember, electrons basically have no mass either because they're so tiny. But their motion and their behavior is more wave-like. So again, we bring this up just to try to be as accurate as possible about how light works. I also bring this up so I can end today, which again, I'm sorry with all the notes. We can end it on a joke. And isn't that the most important thing? If you learn nothing today, you will learn a very corny chemistry joke. So you don't have to write this down. Why doesn't a photon bring luggage on vacation? Because it's traveling light. Thanks, Randy, for at least